So what, I mean, let's talk about it. What are we looking at here? We're looking at we've got 4-dimensional context, right? 2 equations, right? So this is a what? This is a surface in 4 dimensions. Okay. Now, so let's see here. What would could we parameterize this thing? What would can you guys think of how we would? I want to view S as you know, equal to f of I'm sorry, S. I meant M. I want to look at M as as in terms of a patch, right? Any ideas? What should we do? How can we patch this thing?
Like a slanted disk or something?
I like that. Let's use, right, so we're trying to basically solve, we're trying to invent parameters that take care of x squared plus y squared equals to 1 and y plus zw equals to 2. This screams at me x equals to cosine theta, y equals to sine theta. It just says, do this, right? And once you do that, everything else kind of falls into place, right? Because if that's the case, then we can solve zw is equal to 2 minus sine theta, right? Which makes z equal to 2 minus sine theta over w, right? And so that suggests to me that we can use the parameterization f of, let's say, I don't know, theta comma w, right? And I would say that that's going to be cosine theta, sine theta. My z is kind of weird, but 2 minus sine theta over w. And then what's w? Well, w. And there you go. That's a patch of this 2-dimensional surface in a 4-dimensional space. Of course, we need to avoid what? All right, this is for parts of M with, so I'm being a little loose, fast and loose with language here, right? I mean, I should really say M contains this, right? To be more pedantic, because you just told me W not equal to 0, right? Apparently there's another one, let's say F2, which we could use theta and z as parameters, right? And there I would use the parameterization cosine theta, sine theta, z, and 2 minus sine theta. Oh, wait a minute. Yeah, 2 minus sine theta over z. This is for z not equal to 0, right?
Do we have to constrain theta to be in like?
If we want to be picky about the continuity, we should not let it go full 2 theta, right? So we're going to be missing a point. I'm trying not to belabor these issues. It's not what I'm after at the moment. But that is the issue. You know, if you want to be careful and actually have continuity on the whole thing and cover the whole thing, those kinds of issues are exactly what make you have to have more than one chart on the whole space, like a lot of times. Yeah. So that would be another patch on M, right, for the points with z equal to z not 0. But w could be 0, and here it would be fine, right? And yeah, to be clear, we should also tell what theta ranges over. Okay, so the next idea that I want to talk to you guys about is tangent space and normal space. So what should the tangent space to a manifold be? Here, I'll draw a picture. So this is the manifold, right? If I take a point P here, right? And if you just think about tracing curves, you know, that go through that, then those curves will have tangent vectors, right? And if the surface is differentiable at that point, the collection of all these tangent vectors should form what we call the tangent space to P at M. Right? So we can say that that's basically the set P, comma, gamma prime of 0, such that gamma of 0 is equal to P. And gamma a curve. Well, let's say a path on M. So we look at all possible paths on the manifold that go through the point, right? If the manifold is a manifold, then it has a tangent space. In fact, we can prove, and I basically do prove in the notes, I've got fairly decent proofs that this condition, let me sketch the proof for you, all right? Let me explain. And we can go either viewpoint.
Is the tangent space contains gamma prime 0 or also, I mean a pair of it or just gamma prime 0?
I'm saying that we should think of them as being tangent vectors attached to that point.
So it's a vector.
Right.
It's not paired.
So here's basically the parametric viewpoint would be we have, what does it mean to say F? We have F, right, of the path gamma of T is what? That's an element of? True. But more to the point, it's an element of M, which is sitting inside RQ, right? So I'm supposing that it's a path on M, right? So if you differentiate something like this, what does it look like? What happens? We get F prime, right? And then gamma prime of T, right? So and I don't know if you guys may not have heard me say it. The claim I'm making right now is that an n-dimensional tangent space, n-dimensional manifold, will have an n-dimensional tangent space. More precisely, I can build the vector space. I can make this into an n-dimensional vector space in the natural way, where we just let the P ride along and we add the vector parts. So like the rule is P comma V plus P comma W is P comma V plus W, all right? We also have other things, like we can take dot products in here. If I take P comma V dot product P comma W, that's just V dot W. So the P is just decoration. It's really just to remind us that those tangent vectors are attached to the point P. We just usually make the custom of not writing that down in Calculus 3 in physics, even though we really are thinking about tangent vectors being at points, aren't we? This is the abuse. Look at this, though. So we're thinking about all possible paths. All possible paths on the manifold. Can you see why that must be an n-dimensional? Why it must give us first of all, how do you say this? Why it must produce n linearly independent vectors from this, and why it can't produce more. Like, can you have a matrix with rank n, right? And somehow take linear combinations. Remember, this is matrix column multiplication. We're forming linear combinations of the columns of this with these. Can I have more than n linearly independent vectors from a rank n thing? No, I cannot. We're building vectors from these n linearly independent columns. And because we're looking at all possible curves, we can go in all possible directions, and so we actually do fill out the whole tangent space. On the flip side of things, if you look at G, right, and you're looking at, well, so the question is, how do you describe a curve on implicitly? How do you describe a curve on an implicitly defined manifold? That's harder. I have an argument in the notes. And you know what? Maybe I'll come back to it next time. In the meantime, I'll let you read it. But I actually do try to carefully argue that if we have the sort of the codimension, the rank condition over there, I'll trace through the argument, actually. Maybe I should just do that. What that means, right, if this condition is met, that means that we can write points on the surface. We can write y as a function of x. So if we find a parametrization of a curve on the surface, then that parametrization doesn't have independent x and y parts. What happens in the x has to determine what happens in the y according to the local functions which solve the surface. And so that's why, even though it looks like you might have more than n dimensions worth of tangent vectors, you don't, because whatever happens in x fixes what happens in y. And the fact that x is n variables will again force the tangent space to be n dimensional. It's not entirely obvious. My notes have a careful proof. It took me a while to really, really flesh that out. Let me not hand wave too much in here. This viewpoint is easier to see. So there's a theorem, though, okay? So the theorem is simply this. If I want to form the tangent space to P, all right, at M, then I can just take the span of, say, partial F, partial P, comma, partial F, partial xi, right? Stink. At the point P. Goodness gracious. Is that,
Which part did you mess up?
P is a, stay away. P is a point on the manifold, but it maps to, the question is where it came from, right? I mean,
Where did you mess up?
skip. Oh. Let us suppose that f. So you know what I'm after. Let's suppose that f of q is equal to p. Okay. So here q would be an element of the domain of the patch. All right. So technically speaking, I guess I have to take this at q, don't I? I mean, the partial derivatives are calculated in the domain, which is q. But I'm attaching those vectors at p, the point of tangency. Annoying, right? And that's such that I equals to 1 to n, right? So the partial velocities to the patch will form a basis for the tangent space. This is what we do in Calculus 3. For a surface, partial x, partial u, and partial x, partial v, those coordinate velocities, those form a basis for the tangent space to a surface. Remember, we take the cross product of them and get the normal? That's the normal space.
But you have to assume that F is injective, right?
Remember, we assume that F has rank n, right?
But I mean, like, if there is multiple Q that F maps to me, then which one will you take?
Kit, stop wasting my marker. I'm almost out of black markers. Like, if you're going to be annoying, do it. This is my good new marker. Dude. Not cool. Here, use this one.
You know you still have a black marker in here.
Look at this propaganda. we do assume F is injective, so that's not an issue, but I know what you're saying. I mean, yeah. There's a good, what? I told you, don't use my black marker.
This is a different one.
All right, fine. But, okay, Kang's issues aside, sorry, sounded wrong, but this will be this will give us n-dimensional vectors, n linearly independent vectors, so we're assuming that we have a rank n patch. So there's like enough vectors to fill out an n-dimensional space, and there can't be more, because that would contradict the rank of F being n. And so then the Daniel, stop. The other idea is that we can talk about the tangent space to P at M, direct sum with what's called the normal space to P at M. This gives us what I would call the tangent space to P at RQ, of RQ. So basically, there's a codimensionality here. This is n-dimensional, all right? This will be Q minus n dimensional. And the beautiful thing is, let me actually show you explicitly. See, we can pick a point. So you guys got to give me a good point on this manifold that I have explicit formulas for. I want to find the tangent space and the normal space for you guys for this example, and then we'll stop for today. I need a point.
Theta is pi over 3, W is 2.
Theta is pi over 3, W is, what do you say, 2? Okay, that gives me, so we're going to call that, that'll be our Q, huh? So what's F of Q? And I guess we better, I'm sorry, I need to make a decision. Oh, that's the question. Which one are we using, or does it matter? Is this point common to both of these patches? Where is it? Oh, so let's go with F then, because I want to buy us some board space here. Yeah? Okay, so we want to look at F of Q. What's that equal to? Again, Q equal to pi over 3 comma 2. So half, right? Root 3 over 2. Ah! You monster. Let's see here. 2 minus root 3 over 2. That sucks. Let's see here. By 2. Yeah. All right, fine. That's actually 1 minus root 3 over 4. It's not that bad. I take it back. You're okay. You're okay, Sam. So your W is 2. You didn't do. That's good. My usual choice is too trivial. Okay, so that. Yeah, I'll do that. I'll do something like that. It'll make it. So this right here is the point on the manifold I want to look at. I want to find the tangent space and the normal space to that. All right. First of all, let's find the tangent space. So to do that, I need to calculate. Stink. I'm out of board space. So what's we should calculate partial f, partial theta, and then plug in the point q. So I'll do the. I won't plug in q just yet. Partial f, partial theta is minus sine theta, cosine theta, minus cosine theta over w, right? And 0. And let's see here, partial f, partial w, right? At the point q, and we still have to evaluate that at q. Partial f, partial w is what? It's 0, 0. Looks like minus 2 plus sine theta over w squared and 1. Still have to plug in the point q. Plugging the point q, what do we get? we're putting theta equal to pi over 3, so we got minus root 3 over 2. Cosine theta is what? 1/2. This is what? Negative 1/4. Thank you. This is, well, 0. I can do that one. And next, I'll do the first two. And then, so minus 1, you say minus 1/2. What is it? You just said it. Minus 1/2 plus root 3 over 8. Okay. And then 1. Okay, so if I call this thing V1, if I call this thing V2, just for the sake of not writing them again, then TPM is the span of P comma V1 comma P comma V2. That will give me the tangent space to M, just like that. The normal space theorem we'll prove next time. The normal space is given to us in the other viewpoint easily. Like you already know this from, oh, I erased it. Oh, well. So the normal space, check this out. So the gradient of G is what? What do we got for, oh, I'm sorry, not gradient. I'm an idiot. What's G prime? Partial G, partial what? Partial G, partial X. Partial G, partial Y. Partial G. But more to the point, that's the wrong way to look at it. This, for me at the moment, is the gradient of G1, gradient of G2, transpose stacked on top of the other one transpose. Thanks, Dan. So this was, we got ourselves a 2x, we got a 0, we got a 2y, we got a 1, we got a 0, we got a thinking W. We've got a 0. We got a Z, right? So what's G prime of P equal to? Ah! It's not bad. It's not bad. G prime of P is that. So x is 1/2. 2x is 1, right? Then there's a 0 here for free. 1 here for free. 2y is what? Root 3. Actually, Sam, I'm liking this point you gave me. It's actually pretty nice. I'm liking it. It's not bad. It's not bad. And then 0. Oh, I got that one. W. W is 2. Oh, 2. Okay, thank you. And then 0. And then Z. All right, finally the Z. 1 minus the square root of 3 over 4. Okay? So, V3 equal to 1 root 3, 0, 0. V4 equal to 0, 1, 2, 1 minus the square root of 3 over 4. Okay, you use these two things. The normal space to P at M is going to be the span excuse me, of P comma V3 and P comma V4. Now, so this notation, Travis, what this means is that, what I really mean here is that the normal space to P at M, it's what's called the perp of the tangent space to P at M. It's the set of all vectors which are perpendicular to vectors in here. So the normal space, for example, to a plane in calculus 3, it's the normal line. We're trying to generalize that idea so that if we're in like a 10-dimensional space and we have a 4-dimensional surface, then there's like a 6-dimensional normal space. They're always like codimensional. They come together to give you the full dimension of where you're working. So here, we're working in 4 dimensions. We got a 2-dimensional surface. We expect a 2-dimensional normal space. these fill it out. Now, if we did this, now here's the moment of truth, then we can leave. I hope it works, because otherwise I'm going to have to fix it, and we'll blame Daniel. If we did this right, if we haven't made a mistake, right, these are supposed to be perpendicular spaces, as judged by, what's the inner product? It's the forget the point, right? It's P comma V dotted with P comma W equals to V dot W. This is how we take dot products. We just dot product the vector parts. So like, what I'm really asking is V3 perpendicular to V1? It is. Look, minus root 3 over 2 plus root 3 over 2. Dot product 0. Is V3 perpendicular to V2? Look at that. Zeros, zeros. How about V4? Is V4 perpendicular to V1? 1/2 minus 1/2 plus 0. Otherwise known as dot product of V1 and V4, 0. Dot product of V1 and V2. That requires thinking. Not too much. So this 2 times that is what? Minus 1 plus root 3 over 4. Then over here we get 1 minus root 3 over 4 sums to 0. So you notice I was able to do all of this without linear algebra. Why? Because I found both the implicit and the parametric, the patch for the surface. If you just have one or the other, then you have to use linear algebra, something called the orthogonal complement. And there's a way of finding this thing from those things, doing a simple matrix calculation I'll describe next time. We take the transpose of the basis and calculate the null space. It's a standard like row reduction thing. Yeah, that is something we have done. At least I do in 321. I can't promise everybody does it in 321, but so so if you really understood this example, you can do modulo that orthogonal complement thing. This means we can calculate normal spaces and tangent spaces to cool. You just threw 4 airplanes at the same time. But we can find tangent spaces and normal spaces to any dimensional surface you like. And we don't need cross products to create normals because linear algebra, the orthogonal complement, creates normals, right? Or sneaky parameterization versus equations working together to avoid linear algebra creates normals or in tangent spaces, yeah.
So, I think it's safe to assume that this will be like a test question of some sorts in the future.
I do seem somewhat excited about it. Yeah, that's true.
Yeah. When you're given the initial conditions of like the x squared, y squared equals 1, and y plus w equals 2.
Yeah.
Obviously in this case you could say that x is cosine theta, y is sine theta.
This is given. Yeah.
Yeah, but is there like a way to determine a really good parameterization for anything, or do you just kind of have to power guess?
That'd be sort of like going to Michelangelo and asking him how to paint. Parameterizations are an art. There are some general patterns, but there's not a procedure that I know of. You can use, fine. If you want to be ugly, right, you can always try to use Cartesian variables as parameters. And there you come close to having something close to an algorithm. You should aim that way. They always go really far that way. So you should throw them at Jonathan, then they'll actually hit Travis. But
Nobody here's doing this. What a bad teacher you are.
anyway, we'll do more of this next time. In this world, it's really easy to explain Lagrange multipliers and a few other things, but I'll try to do another example. It's a good question. It's kind of like integration, though. The real answer is you got to just kind of get exposed to more examples. There are some general things, like if you got sum of squares, use sines and cosines. You got a difference of squares, use cosh and sinh, you know. If you've got some kind of product like that, you're probably going to need to break up into cases where things are 0. You'll have different, different charts.
Would, using the strategy differential equations, I don't remember off the top of my head, but like kind of breaking it up into vectors and so on, like UV and stuff for that.
Huh.
Help in this case.
I don't know. I have a really interesting one. I'll try to give you guys this as a homework. I forget which direction I have. I either have a patch on the Mobius strip. You guys know the Mobius strip? Yeah. I either have a patch on the Mobius strip or I have equations which define them. I think I have a patch on the Mobius strip. It's actually a very interesting reverse question to find the equation or equations which define the Mobius strip. Whoa, that's fast.
I can keep 4 of them.
They got glasses, so you can't really get them. All right, I think I should stop before we get hurt. All right, that seems like a good place to stop.